Okay, this will be the last of our derivative rules. It's kind of 3 sections in one because none of these is extremely long. So it's 6.1, 6.4, and 6.5 all wrapped into one. We're going to talk about natural log derivatives, inverse trig derivatives, and then how to use what's called natural log differentiation. So we're going to investigate and apply inverse derivatives and derivatives of natural logs and natural log differentiation, as we said. So let's start off with, we're actually going to start off with the inverse trig stuff. So in order to calculate the angle using trig functions, you have to use the inverse trig function. Whoops. You have to use the inverse trig function. So for example, if it says sine of theta equals 1/2, in order to solve for theta, we need to take the inverse trig of 1/2. So we need to do the inverse sine of 1/2. We're actually solving here for theta. So when you're given that little symbol right there, the -1 looks like an exponent, that's your inverse. It means that whatever's inside of there would have been the result of taking the sine of some angle equals 1/2. So you have to ask yourself, okay, what would the angle be that would give me 1/2? Well, we have to remember a few things. We have to remember with inverse trig, we have to restrict the domain. And that's a really important concept here. So you've got two different ways to look at it. You got basically your unit circle way of looking at it. And then we have a graph way of looking at it. So if you remember, your sine function on the graph looks something like this, from 0 to 2 pi, but then it also goes backwards and looks something like that. Extend that graph out there a little bit. So that would be basically from -2 pi to 2 pi on the graph that I've shown right here. Well, in order for you to actually have an inverse, which is a function, it has to pass more than just the vertical line test. It also must pass the horizontal line test. From this reason, this is why we have to restrict the domain. Okay, we're always going to use the first quadrant, or basically in this case from 0 to pi halves, and that would be up to here on the graph. So we're going to use 0 to pi halves right in here. That's part of it. But we also need to include all the negative values of sine. Well, you can't break it and skip it and then come down to here. Oops, and come down to here. Okay, it's got to be consecutive. So we're going to delete that because that's not where it is. So we need to go back into the negative, what would be the negative first quadrant, to here. So we got to go from negative pi halves to pi halves. Now, if you look at that blue section, it passes both the vertical and the horizontal line test. Therefore, the inverse of this is also a function. If you look at your unit circle, we're talking about from negative pi halves, which is down here, up to pi halves. Big distinction here, though, is that we have to, in terms of inverses, this is negative pi halves. We're not going to call it 3 pi halves because 3 pi halves means that you would have gone literally all the way around here, and you can't do that because we can't go through these two quadrants right there to get to the 3 pi halves part. So again, this is just a little bit of a review, so let's get rid of that because that's not right. So sine itself is restricted. Its domain for inverse sine is going to be from negative pi halves to pi halves. Okay, so anything that goes this direction would be the negative first quadrant. Anything that goes that way would be the positive first quadrant. Easier to look at it on the actual sine wave itself. You can see that how easily those things connect from negative pi halves to pi halves. All right, so if I want to figure out what the inverse sine of square root of 3 over 2 is, you might just want to ask yourself, well, what is the sine of what gives me square root of 3 over 2? And that's going to be the angle pi thirds. And I know it's got to be positive pi thirds because the square root of 3 over 2 here was positive, meaning that had to come from what would be your first quadrant. Same general idea for cosine. However, cosine is restricted, if you remember correctly, from 0 to pi. And I'll just do a really quick sketch of cosine. Cosine is the one that starts up here at 1 and then comes down like this and then goes back up. And the reason it's restricted from 0 to pi is because if I trace from 0 to pi, I've got all the positive and negative values of cosine consecutively. So I can simply go from 0 to pi and be perfectly fine. So the inverse cosine of 1, well, cosine would give you 1 at 0. It would also give you 1 at 2 pi, but we don't go that far because it's not a part of the inverse. So this is simply going to be 0. And then tangent, I have to do a little more vertical here because tangent, if you remember correctly, looks like this. And it's got asymptotes at the pi halves. So this would be pi halves, oops, negative pi halves, excuse me, that would be pi halves. So as you can see, tangent already has all of its positive and negative values in that range. So it's also going to have the same domain as sine with one exception. Sine can include the pi halves. Tangent cannot include the pi halves, and that's because those are asymptotes. Tangent doesn't exist there. And the inverse tangent of 1, again, is asking yourself, tangent of what angle is going to give me 1? And if you remember correctly, that was at pi fourths because it's where sine and cosine are identical. When you divide sine and cosine, you would get 1 there. All right, so that is a basic recap of inverse trig functions. Okay, you didn't really need that specifically for the derivative, but it is going to help in the long run to understand what's going on. All right, so we've got our derivatives of inverse sine, inverse inverse tangent. I don't have anything on here for inverse cosine, secant, cosecant, or cotangent. And the main reason is it's not because they don't exist, it's because they're not tested on the AP test. It's something that we can come back to at some other time if it's necessary. So I'm just going to keep it for inverse sine and inverse tangent for right now. So the derivative of inverse sine of x. Okay, as much as I hate to say just know this, you're going to want to memorize it. I am going to prove this actually at the end of the lesson, just to let you know it's not just coming from nowhere, and it actually does. There's a reason why it is this, but to develop it and to try and figure it out as you go, too long of a process. So you're just going to want to know these. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. And that's it. The derivative of inverse tangent, very similar. 1 over x squared plus 1. Or you could write it as 1 plus x squared. Notice that they're very similar. They both have 1 over. The sine has a square root in it. Tangent does not. The tangent one is positive. Sine is negative. I'm not sure what the best way for you to go about knowing those, but you will need to know these two. The tangent one is going to occur more frequently, but you're going to need to know both of them. Now, this is okay. This is both the case as long as these are just x. As soon as we put something else in there other than x, some other function of x, like maybe it's, inverse sine of 5x squared, then the chain rule comes into play. So that's where we're going to scroll down to here. If we say that u is some function of x in this case, that means you're going to have to apply the chain rule. Okay, it's no different than the chain rule that we've been doing before. You would take the derivative of the inverse sine part, and you're going to get 1 over square root 1 minus u squared. Whatever is there in that place, it's going to get squared. But the chain rule then says I have to multiply by the derivative of u because u is a function of x, so it's times u prime. Okay, same idea with tangent. 1 over 1 plus u squared times the derivative of u, which is u prime. And if you think about it up here, it works the same way. if I did 1 over square root of 1 minus x squared times the derivative of x, that's 1. So it still is holding that chain rule. We just don't usually have to write the times 1 part. All right, so there are your two derivatives of your inverse trig functions. Okay, now let's go ahead and look at derivatives of logs. Now, it does say here by the flashcards, those have not been given to you yet. And if they have, then it's a different time. But by the flashcards, which you will eventually get if we don't have them already, the derivative of the natural log of x is 1 over x. That's what it says. But now we're going to actually show why this is. Okay, so the derivative, oh, I'm sorry. We're actually going to come back to that part showing why. Now let's go ahead and do it right now. Why not? So the derivative of the natural log of x. Okay. Let's start off with the fact that y equals the natural log of x. That's our function. We want to take the derivative of that. If you remember from pre-calculus stuff, we can change this into an exponential. Remember that the base of a natural log is e. So I could rewrite this as e to the y equals x. Right? The whole idea here is that's e. So you can rewrite it e to the y equals x. So e to the y equals x. We know how to take the derivative of an exponential. We know how to take the derivative of x. So now let's go ahead and take the derivative of both sides of this equation. Well, the derivative of e to the y, that's an exponential. It says rewrite it, times the natural log of the base, the natural log of e is 1, times the derivative of the exponent. But remember, y is a function of x. So the derivative of y is dy over dx. And then the derivative of x is 1. We can solve that for dy over dx. So dy over dx is 1 over e to the y. But what is e to the y? E to the y is x, according to that equation. So that can be rewritten in terms of x as 1 over x. And there is the derivative of the natural log, 1 over x. So that is why the derivative of the natural log is 1 over x. Very much like what I just talked about in the previous inverse trig derivatives. If the x of the natural log of the x, if the argument is not something which is just x, and it's some other function of x, so we're going to, again, assume that u is a function of x, then the derivative of the natural log is 1 over u times the derivative of u, which in this case would be u prime. So the easiest way to remember it, and this is kind of the way I say it, is the derivative of a natural log is always 1 over the argument, whatever you're taking the natural log of, times the derivative of the argument. 1 over the argument times the derivative of the argument. That's how you take the derivative of a natural log. Of course, that sounds really simple, like it's only two things to remember, but the argument itself could be something much more challenging where you have a quotient rule or a product rule or something else going on in there. So it could be a lot to keep straight. All right, we don't see the derivative of regular logs too much, but this is the derivative of a regular log. So the derivative of a log of x base a is 1 over x ln of a. Again, this is not something you see very much. If you choose to memorize it, that's fine. It can be developed. It's not extremely hard, but it takes a few steps. So we're going to start off with the log of x base a. This can be rewritten using one of the properties of logs, which is called a change of base formula. We can use the change of base formula to write this as the log of x divided by the log of a. And the base doesn't matter. In this case, the way I have it written, it's base 10 because that's understood, but it could be anything. I could write this as the log of x base 6. Makes no difference. That's the nice thing about the change of base formula. Oops, that should be an A on the bottom. That's the nice thing about the change of base formula is it doesn't matter what the base is. That being said, I could also write these as logs with base e, but we call those natural logs. So I could call this the natural log of x over the natural log of a. One thing you have to remember is that a in this case is just a constant. It's just a number. It's whatever the base of the log was. It's a positive whole number of some kind. So I can write this as 1 over the natural log of a times the ln of x. 1 over the natural log of a is just a constant, and it's a coefficient in this case. So we're going to pull that out as a constant. Then I know that the derivative of 1 over the ln of a, ln of x, I can pull the constant out, or basically just treat it like a coefficient, times the derivative of natural log of x, which we just figured out above was 1 over x. So what we get is 1 over the ln of a times 1 over x. Multiplying those two denominators together, you get 1 over x ln of a. And that's it. Again, this doesn't occur that frequently in the stuff that we see, but that's how you would take the derivative of a regular log. You can either choose to do it as just memorizing the formula, or you can convert it by using change of base formula into natural logs and then take the derivative there. All right. So let's go ahead and do a little bit of practice on these two specific properties with inverse trig and log properties, just to see what we're doing here. So the first one says, calculate the derivative of the natural log of x squared plus 10. Well, according to our rules for taking derivatives of natural logs, it's 1 over the argument, 1 over x squared plus 10 times the derivative of the argument. The derivative of x squared plus 10 is 2x. So just kind of cleaning that up, it's 2x over x squared plus 10. That's it. That's the derivative of that one. Not too difficult there. The next one is a regular log. So once again, you could change these into natural logs or just kind of memorize the property. It's really up to you. I know that it's going to be 1 over x, x being the argument, times 1 over ln of a. The a is 10. So it's 1 over the ln of a times, now I'm just going to do the derivative of x over x minus 1, just like it was a natural log of that. So it's 1 over that. So when you take 1 over a fraction, it really flips the fraction over, it reciprocates it. So what I'm going to get out of that is x minus 1 over x. That's the 1 over the argument part, times the derivative of the argument. Don't forget, this is your argument, not what you just flipped over. So now I have to multiply this by the derivative of x over x minus 1, which itself is a quotient rule. So it's going to be the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over bottom squared. So if I want to clean this up just a little bit, I can. It's going to be 1 over, oops, that shouldn't have been ln of a, that should have been ln of 10. ln of 10 times x minus 1 over x times, up here we're going to get an x, a minus x, those are gone. We're going to get a negative 1 over x minus 1 squared. And it looks like I can get rid of that x minus 1 and one of the x minus 1s from the bottom, so that gets rid of the square. So it looks to me like the most simplified version of this might be negative 1 over x minus 1 ln 10. Okay, really, technically, you could have stopped at that step right there, and that still would have been your derivative, but the boxed one is the most clean version. Okay, why does taking these natural log derivatives kind of help? Well, we'll get to some more complicated problems as to why. But if you look at this one right here, natural log of the 5th root of x, I could do 1 over the 5th root of x times the derivative of the 5th root of x. Or I could use log properties, which is going to be smarter in this case. to say, okay, I can rewrite this as natural log of x to the 1/5 power, because that's what a fifth root is. And then if you remember, since I have a power on my argument, I can bring that out to the front of the natural log. So that'll be 1/5 of the natural log of x. This is going to be much easier to take a derivative of. So the derivative of 1/5 the natural log of x, remember that 1/5 is a coefficient, just stays there. Derivative of natural log of x now is 1 over x. So this is 1 over 5 times 1 over x, or 1 over 5x. Okay, again, you could have done it the other way. 1 over the 5th root of x times the derivative of 5th root of x. Believe it or not, it does simplify to this. It's just a lot messier. Okay? And then this next one, next one is actually an exponential. Okay, we didn't actually cover exponentials in this particular section, but we're going to go ahead and practice them. And the main reason is because they're so closely tied with logs anyway. So remember, for an exponential, the rule was rewrite it times the natural log of the base, which is the natural log of 10, times the derivative of the exponent. Derivative of tangent is secant squared theta. And that's it. You could put it in a different order if you want to, but that's it. Nothing combined. So you're good to go there. The last one I kind of like because it looks menacing. Well, it's not the last one, but number 5 here. I kind of like it. It looks kind of menacing, although it's not as bad as you would think. You just have to kind of be careful because it looks like we've got an exponential within an exponential. So it's going to be an exponential of a chain and all this kind of other stuff. It's going to be fun. So let's take a look at it. I have to treat this as, first of all, the exponential is 2 raised to some power with x's in it somewhere. So it's going to be an exponential function to start off with. So y prime says rewrite it 2 to the 3 to the x squared times the natural log of the base, which is 2, times the derivative of the exponent. Well, the exponent itself is 3 to the x squared, so it's another exponential. So when I do the derivative of the exponent, now I'm doing the derivative of another exponential. So start over again. So it says rewrite it 3 to the x squared times the natural log of the base, which is the natural log of 3, times the derivative of the exponent. Derivative of x squared is 2x. Again, looks kind of ugly, but that's it. And all of this right here is the derivative of the exponent of the base of 2 part. So there you have it. Long derivative, but that's what it is. All right, and then the last one we'll do before we'll stop this one and come back with another video. Y equals natural log of x over x squared. Quotient rule. Derivative of the top, 1 over x, times the bottom, x squared. Minus derivative of the bottom, 2x, times the top, natural log of x, all over the denominator squared. Okay, let's clean this up. 1 over x times x squared is x, minus 2x natural log of x over x to the 4th. And it looks to me like I have an x in every term, so I can cancel an x out of there. That becomes a 3rd power. So what I'm going to get now for my final answer is 1 minus 2 natural log of x over x cubed. And that's going to become important that we can do that, because there are going to be times we're going to have to simplify those for further use, especially with applications later on. All right, that is plenty long enough for this video. We'll come back. We'll do some examples using inverse trig, and then we'll get into our the rest of our inverse derivatives and our application.